I mentioned before that even though rounding errors are tiny, their accumulation can still become a problem. But this might sound strange at first, because rounding errors are sometimes above and sometimes below the true value, so one could think, shouldn't they just cancel out on average? Well, let's try a small experiment. We start at 0. Then we flip a coin. If it lands heads, we add 1. If it lands tails, we subtract 1. So, after one step, we are either at +1 or at -1. After 2 steps, we might be back at 0. And after 100 steps, well, let's run it. And we get some value. Maybe it's 6, maybe it's -12, maybe it's 2. But usually it is not exactly 0. And obviously you will say, well, that was one attempt. For statistics you need many repetitions of the experiment and see what is the average. And you would be right. So let's run the same experiment again and again. We just need to be careful, as we do not care if the value is positive or negative. We just want to know how far it is from 0. So we need to take the absolute value. Now something interesting happens. For the 100 coin flips, the typical distance is not 0. It is somewhere around 8. Maybe we did not take enough samples, so let's increase it. Again, a similar result. Now let's increase the number of flips. 100, 1000, 10,000, 100,000. The distance grows. If we plot it, we see something very familiar. It fits nicely to a square root of n scaled by some constant. What we just made is a one-dimensional random walk. At each step, we randomly move 1 unit to the left or 1 unit to the right. And one of the most important facts about this random walk is the average signed position stays close to 0, but the typical distance from the start grows approximately like square root of n. This is the key idea. Random errors do cancel in one sense. They do not create a preferred direction, but they do not disappear. They spread out, and that spreading grows like the square root of the number of steps. That is why rounding errors can become a problem. A single rounding error is tiny, but a large computation can involve millions, billions, or even trillions of operations. If every operation gives the result a tiny random push, then the final error behaves like a random walk. So the more complex our calculation becomes, the more our final precision can be limited by these accumulated errors. And to understand why this happens, we need to understand random walks. So why does something with no preferred direction still move away from the start? At first, that sounds a bit wrong. If left and right are equally likely, shouldn't everything just cancel out? Well, yes and no. There are two different things that we can average. The first one is position. If the worker ends up at +8, its position is +8. If it ends up at -8, the position is -8. And if we average many works, those positive and negative positions can cancel. So the average position can be 0, but the distance is different. If the worker ends up at +8, the distance from 0 is 8. If it ends up at -8, the distance is also 8. There is no such thing as negative distance. So when we average distances, there are no negative values that can cancel the positive ones. So that explains why the average position can be 0, while the average distance is not. They are just different questions. One asks, where did we end up? And the other asks, how far away are we? Now there is another way to see the same thing. Imagine if the worker is already at position 5. After one more coin flip, it can move to 6 or to 4. So one step takes it further from 0 and one step takes it closer. The average distance is still 5. So nothing changes on average. The same works on the other side. If the worker is at -5, one step takes it to -6 and one step takes it to -4. Again, one step further, one step closer. Average distance stays the same, but 0 is different. If the worker is at 0, then both possible moves take it away from 0. Heads gives +1, tails gives -1, but both are distance 1 from the start, so 0 is a special point. Whenever the random walk comes back to 0, the next step has no choice but to move away. And that is where the average distance gets its extra push. You can see it with a tiny example. Suppose we start at position 1. After one step we can be at 0 or at 2. The average distance is 1. So after one step, the average distance has not changed. But now take one more step. From 2 we can go to 1 or 3. From 0 we can go to 1 or -1. So the possible distances are 1, 3, 1, 1. And the average is 1.5. Now it increased. So the worker does not suddenly prefer one direction. It increases because one of the paths comes back to 0, and from 0 both next steps move it away. 0 behaves like a special point. As the walk spreads out, coming back to 0 becomes less likely. If we are already far away, you need many lucky steps in the right direction to return. So the average distance still grows, but it grows more and more slowly, which means that it grows not proportional to n or faster, but like a function whose derivative is a decreasing function. The graph still goes up, while its slope gets smaller and smaller. And to figure out that function, we need first to see what is the probability to end up at a certain distance from the start. So let's look at the possible final positions. After n coin flips, suppose we get k heads, which means we moved right k times. And since there are n steps in total, we moved left n minus k times. So the final position is x equals k minus n minus k, which gives x equals 2k minus n. So if we know the number of heads, we know the final position. For example, if n is 10 and we get 6 heads, then we also get 4 tails. So the final position is 2. And now, how likely is it to get k heads? To answer that, we can use the binomial distribution, which tells us what is the probability to get one of two possible results k times in n attempts, if the probability of getting that result in one attempt is p. In our case, the probability of going left or right is the same, so p is 0.5. The probability of getting k heads in n coin flips is given in this equation, so the probability of ending at position x is connected to this by k equals n plus x divided by 2, which means that the probability of ending in position x after n steps is this, as long as that number of heads is actually possible. And now we can write the average distance. We take every possible final position, take its distance from 0, multiply by how likely it is, and add everything together. So we get this. Or written using the number of heads, we get this equation. This is the exact answer, and it is not very nice looking. So instead of staring at this sum forever, we can use a nice property of the binomial distribution that lets us approximate it with a normal distribution when n is large. This approximation works best when n is large and neither outcome is too rare. In our case, p is 0.5, so we are in the nicest possible case. To determine the shape of the normal distribution, we need some characteristic values for it, which we can calculate based on what we learned from our random walk till now. So, as we mentioned before, the average step is 0. But as the step has a finite size, that is, it is always 1 for the square, for each step we get 1. So the average squared step is also 1. That means the variance of one step is 1. And when we add independent random steps, the variance is said, which means that after n steps, the variance is sigma squared equals n. And the standard deviation, which is related to the width of the bell curve, is the square root of that. This is why the distribution gets wider like square root of n, by every step adding a little bit of spread. Using the obtained values, we can approximate the final position width in this equation. So, this is the normal distribution centered at 0 with variance n. The center is 0 because left and right are equally likely, and the width is a square root of n because the variance is n. Now we can calculate the average distance from 0. Distance means absolute value, so we want this. Using the normal approximation, this becomes an integral. This looks a bit scary, but the idea is simple. For every possible final position x, we take its distance from 0, multiply by how likely it is, and add everything together. The integral is just the continuous version of that sum. And since the normal distribution is symmetric, the negative side and positive side give the same contribution. So you can write, now, we only need to solve this integral. We can pull out the constant, and this integral has a nice form. And if we define u to be x squared divided by 2n, then we can use this, so the integral becomes this. And finally, we can simplify it to this. So the whole integral is just n. Putting that back in gives us the following result, which simplifies to square root of 2n divided by pi, or approximately 0.798 square roots of n. And this is the result that we saw in the simulation. As for 100 steps, this is approximately 7.98, which is why the typical distance was around 8. So now we can say it more precisely. The average signed position is 0, but the average distance from 0 is approximately square root of 2n divided by pi. So the walk does not drift in one direction, it spreads. And the size of that spread grows like square root of n. Now we can finally translate this back to rounding errors. In the random walk, every step had the size 1, but a rounding error is much smaller. So let's say that every calculation introduces a small error, ei, where I tells us which operation produced that error. If the rounding is unbased, then sometimes the result is rounded up and sometimes it is rounded down. So the simple model is to say that each error is randomly chosen between minus epsilon and plus epsilon, where epsilon is the largest possible size of one rounding error. So the error is uniformly distributed in this interval. This means that every value between minus epsilon and plus epsilon is equally likely. So the probability density is 1 over 2 epsilon for e between minus epsilon and plus epsilon, and 0 outside this range. This is the main difference compared to our one-dimensional discrete random walk. Here, every step was either 1 or minus 1. Here, the step can be any tiny value between minus epsilon and plus epsilon. Now, to find how the average error grows, we need the characteristic values of this distribution. Because distribution is symmetric, the average rounding error is again 0. So again, there is no preferred direction, but the error still has a size. To measure this, we can calculate the average squared error using this integral, which we can simplify in this form. So as the integral of e squared is e to the third over 3, we get this result. And finally, we get epsilon squared over 3, which is the variance of one rounding error. And with that, the standard deviation is epsilon or square root of 3. Now, suppose we do n operations, with each one adding one small independent rounding error. The total error is the sum of all the rounding errors, and since the average of each error is 0, the average total error is also 0. So the result does not drift up or down on average, but the variances add. So after n operations, we get n epsilon squared over 3, and with that the standard deviation is epsilon square roots of n over 3. And this is very similar to the random walk from before. The only thing that changed is the constant. The square root of n is still there. Now for many operations, the total error starts to look like a normal distribution. Finally we can write, well, sigma e squared is n epsilon squared over 3. So in the end we get this. This tells us the shape of the final error cloud. It is centered at 0 and its width is proportional to epsilon square root of n. Now, just like before, we can calculate the average absolute error using the normal approximation. For a normal distribution centered at 0, this integral gives us sigma e squared square root of 2 over pi. And since sigma e is epsilon square roots of n over 3, we finally get epsilon square roots of n over 3 square root 2 over pi. This is the average size of the accumulated rounding error in this simple model, when n is large enough for the normal approximation to work well. So if each individual rounding error is uniformly distributed between minus epsilon and plus epsilon, then after n independent operations, the signed error cancels on average, but the size of the error does not vanish. It spreads. Of course, this is a nice case. It assumes that the rounding errors are independent, unbiased, and roughly uniform. Real calculations are not always that nice. Sometimes the same error repeats, sometimes the errors are based, sometimes an algorithm amplifies small errors, and then the error can grow much faster. And about some of those interesting cases we will talk in the following video, so make sure to like and subscribe if you do not want to miss it. See you next time and have a fantastic day.